This is Puppis A. It is another type 2 supernova remnant. You can see the neutron star in the core here. And this one, again, looks very, very different too. So Puppis A is actually expanding, obviously, into interstellar medium that's lumpy and bumpy. And so that some places its advance is impeded by the clumps in the interstellar medium, and it gives it that pitted kind of cratered look to the surface. This is the mother of all supernova events, the SN 2006 GY event. This image is an infrared image from the Lick Observatory, and in the center is this galaxy. And if you look closer into the center of that, here is the nucleus of the galaxy, and here is supernova 2006 GY. And if you look at it in X-ray, you can see that the radiation, the X-ray radiation coming from that one supernova event, it's almost as bright as the X-ray radiation coming from a multi-million mass black hole in the center of the galaxy. Well, when you have a star that is more than, let's say, 150, 200 solar masses, really, really massive stars, and they undergo a core collapse, that collapse happens so fast and so catastrophically that the gamma rays produce matter and antimatter that annihilate each other. There's not even time for a core to form. There's no black hole at the center of this. There's nothing at the center, no stellar core whatsoever. All of the material of that star is in the remnant of the star. It looks suspiciously like Eta Carina. Now, supernova 2006 GY was in another galaxy far, far away, like around 238 million light years away. Eta Carina is only 7,000 light years away. It's in the Milky Way galaxy. It's in the southern hemisphere, so unfortunately when it goes, you've got to be in the southern hemisphere to see it. Eta Carina was a 150 solar mass star, and about 20 years ago, well, maybe the late 80s, I think, it ejected a huge amount of mass, about 30 solar masses, and it's only now about 120 solar mass stars left behind. It did not further keep contracting, and it did not go supernova. Nobody's quite sure how it managed to save itself, but it did. But any day, astronomically speaking, Eta Carina is going to go and become a type 2 supernova event, and probably to the same extent as supernova 2006 GY. When it does happen, it will be the brightest object in the entire Milky Way galaxy. And we'll have to go to the southern hemisphere to see it. To show you the difference in energy among all these different types of events, this is a typical light curve for a type 2 supernova event, the core collapse of a massive star. And this is a typical light curve for a type 1A supernova event. They have more energy because they are not a core collapse, they're a thermonuclear explosion. And this is how much more energy was produced from the 2006 GY supernova. This is an artist illustration of Cygnus X1, which was the first detected and confirmed black hole. It's a 14 solar mass black hole with a companion star. This is M33X7, a 16 solar mass black star. When this was detected by Chandra, it was the largest solar mass black hole detected to date. I do not know if anything more massive has been discovered yet or not. But this 16 solar mass black hole is orbiting a 70 solar mass companion. Its orbital speed is about 3.5 days, and you can actually detect from it the stellar winds from the 70 solar mass companion star, how they are being dragged around and fed into the well of space-time produced by the extreme gravitational field of this massive stellar-sized black hole and all of the ripples in the solar wind that are left over from behind. Pretty amazing. This is another black hole, a stellar mass black hole with a companion star, a main sequence star. And Chandra observed it, and okay, it's just another, okay, black hole X-ray binary system. Then they went back and looked at it again 2 months later. And wow, all of a sudden, and they could determine this just by using the Doppler effect, all of a sudden, from this quiescent black hole, there were winds. And those winds were emanating from that black hole at 20 million miles an hour. From zero to 20 million miles an hour, okay, in 2 months. So there is something going on here that is very similar. Now the reason that they spend a lot of time with stellar mass black hole binary systems is that we're really fascinated by AGNs, active galactic nuclei. Very, very energetic, massive galactic nuclei that were formed at the early stages of the universe. So they're all really far, far, far away and hard to study. So, but if you have a massive black hole within a galaxy, very compact with that accretion disk, then it's the very same scenario as that black hole has with the accretion disk surrounding it. So they're very similar in structure. So studying these allows us to learn more about the AGNs. And what seems to be happening is that now black holes have jets of matter and antimatter that spew out along the rotational axis. And sometimes you see those jets, but sometimes you see that wind. And it is not known yet if the jets stop and the winds from the star take over, or does the winds increase from the star and that stops the jets from happening. It's not exactly sure how the jets and the winds are working together. Well, what is known is this: when those winds take over, there is a lot of material, about 30% of the mass of the material in that accretion disk is ejected into space. So this seems to be a mechanism that actually limits the size of a black hole. So no, they do not just get more and more and more massive. There is a mechanism that stops them from accreting more material. This particular system is really fascinating. This is the same kind of a system, an X-ray binary. It is ejecting an X-ray pulse every 50 seconds, just as regular as a heartbeat. Every 50 seconds, an X-ray pulse is emitted from this system. And what they think is happening is this. This black hole is rotating at the maximum speed that a black hole can possibly rotate. That means that the material in the accretion disk is closer to the black hole than the normal situation. And the material is actually so close to the black hole that the diameter of the material is only 20% larger than the diameter of the event horizon. So as that material gets that close to the black hole, the pressure, the radiation pressure from the black hole itself disintegrates the material and ejects it, and that produces the X-ray pulse. And then, of course, more and more material infalls to the center, and it happens all over again. So every 50 seconds, it is disintegrating the material and emitting an X-ray pulse that can be detected. This is a transition of a low-mass neutron star in a binary system into a millisecond radio pulsar. Now, we tend to think that, oh, that's a pulsar, oh, that's a neutron star. But, you know, everything is always continuously changing over time. And low mass, very non-energetic neutron stars can pick up energy and rotate and turn into a pulsar. The other way can happen. Pulsars can lose their energy and end up being a neutron star. That was always known to be true, but the shock in this discovery is that the time frame, in only 7 years, it's gone from the fairly quiescent neutron star and turning into a millisecond radio pulsar. This particular observation was to respond to the galactic X-ray ridge mystery. For about 20 years ago, it was discovered that this is mysterious X-ray glow emanating from the center of the Milky Way galaxy. And it extends with Sagittarius A, centered on Sagittarius A, the black hole. It's stretched for 40 degrees along the plane of the galaxy and 2 degrees above and 2 degrees below the plane of the galaxy. So you have this long rectangular strip, 40 degrees by 4 degrees, centered on Sagittarius A, producing all this X-ray emission. And it couldn't be gas because there's not enough mass there to hold that gas there. It would just dissipate. And there just wasn't any kind of a process that could continuously renew this X-ray plaza. So it was a huge mystery. So Chandra, they did an observation to address this issue. Well, before they launched Chandra, they had predicted that in an area of the sky equivalent to the full moon, that Chandra would detect 200 X-ray sources. Well, Chandra focused in on a 12-day observation, 1.2 degrees below the center of the plane of the galaxy, and during this 12 days observed what they could observe in this patch. This would be equivalent to 3% of the size of the full moon in the sky. Only 3%. And in that little 3% patch, they discovered 473 individual X-ray sources, mostly white dwarfs. So that's what's producing the mysterious X-ray glow. It's not a gas. They are individual black holes, white dwarfs that are emitting X-rays and creating this phenomena.